Okay, so now we're going to move on into section 5, which talks about the chemical properties of monosaccharides. And specifically, we're really just talking about reactions of monosaccharides. So thinking back, we've been talking a lot about aldehydes and ketones when talking about monosaccharides. So let's remind ourselves of the oxidations and reductions of monosaccharides. So thinking back, aldehydes are oxidized into carboxylic acids. Let's change our color real quick. So we know that reaction just oxidizes an aldehyde and it goes to a carboxylic acid. We can also reduce aldehydes. They're reduced to primary alcohols. And then additionally, ketones are also reduced into secondary alcohols. So knowing those foundations of those reactions that we learned back in chapter 12, the numbers are all jumbling up in my head, but knowing and remembering those reactions from chapter 12 are going to help us understand what happens in the monosaccharides as well in these sugars. So the first reaction we're going to learn is the oxidation of monosaccharides. So specifically, we're going to be talking about Benedict's reagent again. So we've talked about this before in terms of a test for aldehydes, or specifically aldehydes with an adjacent OH group. So remember, that's the important part, is that it has an adjacent OH group. And the reason that this was developed with that in mind is specifically for sugars. So we're talking about sugars that can be reduced. So specifically, things that can be reduced are going to be your aldoses, so things with aldehydes on them. So in this reaction, we have that aldehyde, which has a OH group. Oh, I wanted that, dang it. We have our aldehyde that has a hydroxide group right next to it, adjacent to it. And in our Benedict's reagent test, we're going to add our copper ions to it and our oxidant, and we end up getting a carboxylic acid out. So even though we have all of this craziness going on with the rest of the chain of all of the different hydroxides and everything on there, this is going to specifically, or I guess the fastest thing that's going to be oxidized is that aldehyde into a carboxylic acid. So we often will look at these reactions, these oxidation reactions, kind of in a little bit of a bubble, in that there's only one functional group that can be oxidized. And it's kind of overwhelming when you look at all of these molecules, or how big this molecule is. But remember, just looking at, oh, we know how to pretend like the rest of it's just an R group, right? We know how to oxidize an aldehyde to a carboxylic acid, and that's all we're doing. So again, this Benedict's reagent, when you have a positive test, so I guess it's the closest I can get to a brick red color. So when you have a positive test, you reduce your carbon, which is at an oxidation, or not carbon, copper, which is an oxidation state of 2. You reduce it down to copper 0 or copper 1, and it makes this copper 2 oxide complex, which is a brick red color. So a positive test for this is that you go from a clear solution to a brick red solution. So specifically, this test works, as we've talked about, for aldehydes with adjacent OH groups. What those are called are reducing sugars. So a reducing sugar is a sugar that can reduce something else, meaning that it can be oxidized. So for example, a ketose, where you have a ketone as your carbonyl, is not a reducing sugar because you cannot oxidize a ketone any further. It's kind of opposite of what you expect. You see it reducing sugar, so you think it can be reduced, but it's the thing doing the reducing. So the other thing, that means it has to get oxidized in the process. So our reducing sugars are things, specifically aldoses, and this test, this Benedict's test, and overall the oxidation of monosaccharides that we see through this is a test for reducing sugars. The other reaction that we are going to learn is the reduction of monosaccharides. So the exact opposite of, or not the exact opposite, but the opposite overall process of what we're talking about. Oh, I forgot something. We form in these oxidation reactions, we no longer can just call them sugars. We don't have monosaccharides again because that exact ratio is now perturbed. We don't have as many hydrogens as we really should. So these are called sugar acids when we make a carboxylic acid at the end. And we name these a specific way too. So these are, we drop the os and we add onic acid. So for example, the name of this, the product here would be, we started with D-glucose. So then we'll have D-GLUC, and then instead of OSE, we're going to put onic acid. So that's how we name it. So this product is now called gluconic acid. Now continuing on, if we oxidize a ketone or an aldose or a reducing sugar, we can then get to a sugar acid. But if we reduce a sugar, we get to a sugar alcohol. So these, in order to name them, you replace os with etol, ITOL. And really what happens is a same process that we've learned before. We go from a aldehyde and we reduce that aldehyde down to an alcohol. Let's just put a box around the alcohol. So aldehyde reduces down to a primary alcohol. Again, aldehyde reduces down to a primary alcohol using our palladium catalyst and hydrogen. And then just going ahead and naming this. So we had D-glucose to start with. So we're going to have D-GLUC again. We're going to drop OSE and add ITOL. Glucatol, I believe is how you pronounce that. Okay, so another thing, at least in terms of what we use this for in real life, is this is when you see sugar alcohols is a lot of in like diets and stuff like that. So sugar alcohols are not broken down in the body very easily at all. So if you take glucose and reduce it down to sugar alcohol, it still tastes sweet to our taste buds and can sweeten foods. However, your body won't break it down and therefore it can't use it as any calories. So your body just does not process it. So that's why a lot of like diet foods will have these sugar alcohols in them. Okay, so we're going to just go ahead and do these practice problems real quick. Going through, so I do encourage you to try these on your own first and then go through the answers with me. But let's go ahead and look at this first one. So complete the following reaction. Draw the Fisher projection for D-xylonic acid produced when D-xylose is oxidized by Benedict's reagent. So I'm most worried about the product of this reaction in terms of the sugar, but we'll also make sure we draw the copper oxide that we get out of it. So we have a full balanced equation. Let's do blue. Okay, so when we have an oxidant with our copper, that means that we're going to do an oxidation reaction. So this aldehyde I put a box in is what we're going to really react. So I'm going to just draw the rest of this molecule the same. Nothing's going to change about it. These take a little bit longer to draw. Then the box that I did, that functional group that will be changing, I'm going to oxidize that into its carboxylic acid. And then just for good practice, or I guess we're told the name. So this is the name is D-xylonic acid. So all we did was oxidized the aldehyde to a carboxylic acid. And then our reagent left over is our brick red copper oxide. Okay, complete the following reaction. Draw a Fisher projection for D-xylitol produced when D-xylose is reduced with hydrogen and a palladium catalyst. Okay, so looking at this again, the reaction is going to happen at this carbonyl carbon. So we're not going to worry about the rest of the molecule. It's actually just going to be exactly the same as what we had seen before. So I'm going to, oh no, undo. I'm going to cheat a little bit so that it doesn't take too long to, I'm going to try and cheat. I'm going to go ahead and just duplicate this instead of redrawing it. And in that box, now, instead of oxidizing our aldehyde, we're going to reduce our aldehyde. So I'm going to erase everything I had there. And then now we go from a carboxylic acid to, we're reducing, I'm sorry, we started an aldehyde and we're reducing. So we go to our primary alcohol. And we can draw in both hydrogens that we have right there. So now we have an alcohol, and the name of this is then going to be D-xylitol, that sugar alcohol product. Okay, and then our last little problem here is, would the following sugar give a positive result with Benedict's reagent? So Benedict's reagent, if you remember, is the one where it has a positive result when you have an aldehyde with an adjacent hydroxyl group. So in this particular Hayworth structure of our sugar, we don't have an aldehyde. However, you remember that these cyclic molecules are in equilibrium. Technically, it favors the cyclic structure. So I'm going to draw my equilibrium arrows like this. But we need to figure out if this is a aldose or a ketose, because if it's an aldose, then it's probably going to react and have a positive Benedict's reagent test or Benedict's test. But if it's a ketose, it won't, because then we don't have any aldehydes in there. So what we're going to do is we're going to break this bond here that we normally would make in the ring forming process of making our Hayworth structures. So I'm going to draw the exact same molecule, and I'm going to break that bond and form my carbonyl on carbon number 1 right here. I'm going to put a little dot there. Carbon number 1, I'm going to reform my carbonyl at that position and see if it has an aldehyde or a ketone. So I'm going to draw everything else in real quick. Okay, so I'm going to break the bond that I drew a line through. So I'm going to put my OH there. Then I have on the top here, I had a hydrogen. So I'm going to draw that same hydrogen in. And then this alcohol that was at C1 is going to turn into my carbonyl. So I'm going to draw a carbonyl to an oxygen. So now we can see that we have an aldehyde with an adjacent hydroxide. So yes, this will have a positive Benedict's test. Because even though it is in the lesser amount in terms of that equilibrium, you're still going to have it in solution. So you'll have that positive result with the Benedict's reagent. Okay, that is all for these reactions. I'll see you guys in the next video.